So I'll go into some of the details of the vehicle design and performance. And I'm going to gloss over, I'll only talk a little bit about the technical details in the actual presentation, and then I'll leave the detailed technical questions to the Q&A that follows. This is to give you a sense of size. It's quite big. The funny thing is, I think in the long term, the ships will be even bigger than this. I think that this will be relatively small compared to the Mars interplanetary ships of the future. But it kind of needs to be about this size, because if in order to fit 100 people or thereabouts in the pressurized section, plus carry the luggage and all of the unpressurized cargo, to build propellant plants and build everything from iron foundries to pizza joints to you name it. We need to carry a lot of cargo. So it really needs to be roughly on this order of magnitude, because if we say like say a minimum threshold for self-sustaining city on Mars or civilization would be 1 million people. Well, and you can only go every 2 years. If you have 100 people per ship, that's 10,000 trips. So I think at least 100 people per trip is the right order of magnitude, and I think we actually may end up expanding the crew section and ultimately taking more like 200 or more people per flight in order to reduce the cost per person. So, but it's 10,000 flights is a lot of flights. So you really want, ultimately, I think, on the order of 1,000 ships. It'll take a while to build up to 1,000 ships. And so I think if you say, when would we reach that million-person threshold, from the point at which the first ship goes to Mars, it's probably somewhere between 20 to 50 total Mars rendezvous. So it's probably somewhere between maybe 40 to 100 years to achieve a fully self-sustaining civilization on Mars. So that's the sort of cross-section of the ship. And in some ways it's not that complicated, really. It's made primarily of an advanced carbon fiber. The carbon fiber part is tricky when dealing with deep cryogens and trying to achieve both liquid and gas impermeability and not have gaps occur due to cracking or pressurization that would make the carbon fiber leaky. So this is a fairly significant technical challenge to make deeply cryogenic tanks out of carbon fiber. And it's only recently that we think that the carbon fiber technology has gotten to the point where we can actually do this without having to create a liner on some sort of metal liner or other liner on the inside of the tanks, which would add mass and complexity. So it's particularly tricky for the hot gaseous oxygen pressurization. So this is designed to be autonomously pressurized, which means that the fuel and the oxygen, we gasify them through heat exchanges in the engine and use that to pressurize the tanks. So we'll gasify the methane and use that to pressurize the fuel tank, gasify the oxygen, use that to pressurize the oxygen tank. And this is a much simpler system than what we have with Falcon 9, where we use helium for pressurization and we use nitrogen for gas thrusters. In this case, we would autonomously pressurize and then use gaseous methane and oxygen for the control thrusters. So really, you only need 2 ingredients for this, as opposed to 4 in the case of Falcon 9, and actually 5 if you consider the ignition liquid. So we use a sort of complicated liquid to ignite the engines that isn't very reusable. In this case, we would use spark ignition. So this gives you a sense of vehicles by performance, sort of current and historic. I don't know if you can actually read that, but in expendable mode, the vehicle that we're proposing would do about 550 tons and about 300 tons in reusable mode. That compares to Saturn's V max capability of 135 tons. But I think this really gives a better sense for things. The white bars show the performance of the vehicle, like in other words, the payload to orbit of the vehicle. So you can see essentially what it represents is what's the size efficiency of the vehicle. And most rockets, including ours that are currently flying, the performance bar is only a small percentage of the actual size of the rocket. But with the interplanetary system, which will initially be used for Mars, we've been able to, or we believe, massively improve the design performance. So it's the first time a rocket's sort of performance bar will actually exceed the physical size of the rocket.